All right, someone's been doing their AI homework.
Oh, yeah.
I've got research papers here, tech overviews, I see historical notes, even looks like your own personal thoughts scribbled down.
Well, got to make sure we capture all the angles.
I like it. Clearly you're ready to go deeper on this AI stuff beyond just the headlines, and that's what we're here for.
That's right. It has a fascinating mix. You've got everything you need to understand, not just what AI is, but, how we got here and where it might be going.
Exactly. Think of this as your AI cheat sheet, enough to impress your friends at that dinner party, but also to really get why this stuff matters.
Yeah.
So to make it manageable, we'll focus on 3 key areas today.
Okay.
The hardware, the actual, nuts and bolts behind AI, the models that power it.
The brains.
And then some real-world examples that'll hopefully blow your mind.
Yeah, and don't worry, we're going to weave in all the most surprising, interesting bits from, all this research that you've done.
Love it. So let's rewind the clock a bit. Picture those early days of AI research.
Okay.
What comes to mind?
Giant room-sized computers.
Giant room-sized computers.
Yeah, it's like way less processing power than your smartphone.
That's wild, isn't it? Those massive mainframes. How did they even get started with such limited tools?
Well, they did what they could. A lot of symbolic reasoning, expert systems.
Okay, so like trying to teach a computer to think by, encoding logic rules and knowledge?
Yeah, basically. It was groundbreaking work at the time, but, incredibly limited.
Yeah, by the hardware, for sure. So how did we go from those clunky mainframes to the AI we see today? AI that can be grandmasters at chess, write poetry, drive cars.
Right.
It feels like magic, honestly.
It wasn't like a single aha moment, right?
Right.
It was a series of breakthroughs, driven in large part by, the evolution of hardware. Today's AI thrives on something called parallel processing, which is the ability to do tons of calculations simultaneously.
Yeah.
And that requires specialized hardware.
Okay, and this is where I remember reading about TPUs.
Yes.
Those tensor processing units developed by Google. Seem like CPUs and GPUs just weren't cutting it for deep learning. Can you explain why?
Think of your CPU like a multitasking chef in a kitchen.
Okay.
They can juggle several dishes at once, right? But each one is only getting a little bit of their attention.
Yeah.
GPUs are like having a whole team of cooks, much better for parallel tasks, but TPUs are like a whole dedicated bakery.
Wow.
Optimized from the ground up, for the very specific recipes of deep learning.
So it's not just about being faster, it's about being purpose-built.
Yes.
I see. For this complex math behind AI. And there was this note I scribbled down about early TPUs using low-precision computation. What's that about?
Great catch. Early TPUs were actually designed to use fewer bits to represent numbers.
Okay, wouldn't that make the calculations less accurate? I'm a little confused.
No. It seems counterintuitive, right? But deep learning models are surprisingly tolerant to that kind of rounding.
Right.
And the payoff is huge EE.
Okay.
Faster processing, much lower power consumption. It's a brilliant trade-off.
So it's like choosing efficiency over absolute precision.
Right.
Got it. But this brings up another question. My phone doesn't have a giant TPU in it, right?
Right.
How does all this AI magic happen on everyday devices?
You might not have a full-blown TPU, but chances are your phone does have specialized AI chips. Apple's Neural Engine, Qualcomm's Hexagon DSP.
Okay.
They're designed for very specific AI tasks like speech recognition or image processing.
So AI is literally in the palm of our hands.
It is.
That's incredible. This also reminds me of something I jotted down, TinyML.
Oh, yeah.
What is that about? Shrinking AI down even further.
Absolutely. TinyML is about pushing the boundaries of how small and efficient we can make AI. We're talking about AI running on devices the size of your fingernail.
Hold on, seriously?
Using almost no power.
What kind of hardware can even handle that?
Yeah. Microcontrollers, using milliwatts, or even microwatts of power.
Wow.
Companies like ARM, Sentient, they're creating specialized chips just for this, enabling AI on the tiniest of devices.
So we've gone from room-sized computers to pocket-sized powerhouses, and now we're talking about AI running on a chip smaller than a dime.
Yep.
It's amazing.
It is.
Why does that even matter? Why is it such a big deal to make AI so tiny?
That's where it gets really exciting. TinyML opens up this world where AI isn't confined to these powerful computers or smartphones. It means AI can be embedded in almost anything, your clothes, household appliances, even tiny sensors monitoring crops in a field.
So we're talking about an Internet of Things that's actually intelligent.
That's right.
That's a game changer. But hardware's only part of the story, right?
Yeah.
I'm guessing the real leap forward came from figuring out how to make these machines actually learn.
You got it. The hardware provides the platform, but the real magic lies in the models, the algorithms that give these machines the ability to learn and make decisions. And that's a whole other deep dive.
All right, so we've covered this incredible journey of AI hardware.
We have.
From those, room-filling mainframes to those tiny chips powering the future.
Mm-hmm.
But now let's dive into the heart of AI, the models.
Yes.
The models that give these machines the ability to learn.
That's where it gets really interesting. And it's important to remember there isn't just one AI model.
Right.
It's more like it's like a toolbox, filled with different tools, each one designed for a specific job.
So it's not as simple as just saying AI. There are all these different approaches,
Right.
depending on what you're trying to achieve.
Exactly. You wouldn't use a hammer to tighten a screw, would you?
Right.
And in the world of AI, one of the most common tools, especially for complex tasks, are deep neural networks, or DNNs.
DNNs. Okay, those are the ones inspired by the human brain.
Yes.
With layers upon layers of interconnected nodes. But how do they actually learn? It still feels a bit like magic to me.
Imagine a child learning to ride a bike. They try, they wobble, they fall, but each time they adjust, learning from their mistakes, until finally they can ride smoothly. DNNs are similar. They learn through this process called backpropagation.
Backpropagation. Okay, that rings a bell.
Mm-hmm.
I definitely remember reading about it. I got a little lost, honestly, in the technical jargon.
Sure.
Can you, break it down for me?
Yeah.
Explain it as if I were 5 years old.
All right, so think of it like this. The DNN makes a guess, and then we tell it how close it was to the right answer. Backpropagation is like adjusting the knobs and dials inside the DNN based on its mistakes to make a guess better next time.
So it's a constant feedback loop, fine-tuning those connections.
Yes.
Based on how well it's doing. That makes more sense. But I do remember from my research that DNNs have some challenges.
They do.
Like what kind of things can trip them up?
One challenge is something called vanishing gradients. As networks get deeper, the signals that are used to adjust those knobs can get weaker and weaker.
Okay.
It's like trying to shout a message down a long hallway, right?
By the end, it's hard to hear.
So it's a problem of scale.
Kind of.
The more complex the network, the harder it is to fine-tune.
Right.
What are some other challenges?
Another issue is getting stuck in local minima. Imagine, like a hiker trying to find the lowest point in a valley, right? They might get stuck in a small dip thinking it's the lowest point when there's a much deeper valley just over the next hill. Similarly, a DNN can get stuck in a solution that's, not the best possible one.
I see. And of course, training these massive DNNs requires a lot of computational power.
Yes.
Which brings us back to those TPUs we talked about.
Exactly.
It all comes full circle.
It does.
Even with the best hardware, DNNs have their limitations. That's why researchers are always exploring these new architectures, new approaches. And one of the most exciting developments, I think, in recent years has been the transformer.
Yes.
The transformer. This is the architecture behind, ChatGPT, which everyone's been talking about. It's, supposedly revolutionizing natural language processing.
It is. But how does it actually work? Can you give me, the gist, without getting too technical?
Imagine you're reading a book. You don't just process each word individually, right? You understand them in relation to each other. You pay attention to the context, the flow of ideas. Transformers do something similar.
Okay, so they're not just looking at individual words. They're considering, the bigger picture.
Exactly.
I like that analogy.
Yeah.
But how do they actually, achieve that?
Transformers have this incredible ability called multi-head self-attention. It's like having multiple spotlights shining on different parts of the text at the same time.
Oh, wow.
Allowing the model to figure out which words are most important and how they relate to each other.
So it's like the model is reading with multiple sets of eyes, each focusing on a different aspect of the text.
Yes.
That's wild. But words have an order, right?
Right.
A sentence isn't just like a random bag of words. So how do transformers handle that?
That's where positional encoding comes in. It's like giving each word a little tag that tells the model its position in the sentence so it understands the sequence, the flow of information.
So it's all about context relationship.
Yes.
It's like transformers are learning to read not just words, but meaning. Are there other key components to transformers that, we should wrap our heads around?
Well, there are feed-forward layers that further process the information, and there are mechanisms for combining the outputs of those multiple attention heads. But, the core idea is this parallel processing of information with an understanding of context.
That's a great explanation.
Yeah.
Now, I do remember from our source material that there are other types of AI models besides DNNs and transformers.
There are.
Can you give us a quick overview?
Of course.
What else is out there?
You've got generative adversarial networks, or GANs, which are, they're known for creating this realistic synthetic data. Think images, music, even text. It's like having two AI agents competing. One tries to create fake data, the other tries to spot the fakes.
Okay.
And through this competition, both get better and better.
So it's like an AI art forgery game.
Kind of, yeah.
Where the forger gets increasingly skilled at mimicking the real deal.
That's a great way to put it.
That's amazing. What about the other models?
Then you have variational autoencoders, or VAEs.
Okay.
They're a bit like compressing and then decompressing a file. They learn by mapping data to a simpler representation and then reconstructing it. They're used for generating new data, but also for things like anomaly detection, spotting things that are out of the ordinary.
And then finally, we have diffusion models.
Yes.
I remember reading these are all the rage right now
They are.
for generating high fidelity images.
Exactly. Imagine starting with a blurry image and then slowly adding details until it becomes crystal clear. Diffusion models work by reversing this process of adding noise to data, learning to denoise it until they can create these realistic images from scratch.
Yeah. So many different approaches to making machines learn. It's clear that researchers are constantly pushing the boundaries of what's possible. But what I'm really curious about is, how are these models actually being used in the real world?
Well, that's a perfect segue to our next topic, AI in action.
Ooh.
We'll explore how these models are already changing fields like robotics, healthcare, and even our understanding of meaning itself.
Sounds fascinating. Can't wait to dive into that. Okay, so we've talked about the powerful hardware and the mind-boggling models that make AI possible.
Right.
But now let's get to the really fun part.
Yeah.
How is this all actually playing out in the real world?
That's where things get truly exciting. The applications of AI are so diverse, and we're already seeing the impact across so many fields, from robotics to healthcare to even our understanding of meaning itself.
Let's start with robotics.
Okay.
This one really captures the imagination.
It does.
We've all seen those sci-fi movies, right? With intelligent robots. But seeing it happening in real life is something else.
It's incredible to witness, isn't it?
It is.
One of the biggest challenges in robotics is something called motion planning. Figuring out how to get a robot to move from point A to point B in a complex and, ever-changing environment.
I could see how that would be tricky.
Yeah.
For us humans, walking, navigating, it feels effortless.
It does.
But for a robot,
Right.
it's a whole different ballgame.
It is. They need to process tons of information and make these split-second decisions.
Exactly.
And that's where AI shines. Techniques like deep reinforcement learning and imitation learning are allowing robots to learn from experience.
So instead of programmers having to write these detailed instructions for every possible scenario, the robot can kind of figure it out on its own.
That's the idea.
It's like they're learning by doing.
That's the beauty of it.
Wow.
And this is leading to some groundbreaking advancements.
Yeah.
Take self-driving cars, for instance. They rely heavily on AI for tasks like object detection,
Makes sense.
identifying pedestrians, other vehicles, obstacles in real time.
They need to be able to see and understand their surroundings to navigate safely.
Exactly.
Okay, so AI is giving robots the ability to move and perceive the world. What about healthcare?
Okay.
I know there's a lot of buzz about AI revolutionizing medicine.
Absolutely.
Yeah.
One area where AI is already making a difference is in medical image analysis.
Okay.
Those CNNs we talked about, convolutional neural networks, they're being trained on these massive data sets of X-rays, CT scans, MRIs.
I remember reading about this.
Yeah.
It's mind-blowing that these models can learn to spot patterns
It is.
that might be missed by the human eye,
It's possible.
potentially leading to earlier and more accurate diagnoses.
It's truly transformative.
Yeah, and beyond image analysis, AI is also being used to personalize treatment plans
Yes.
by analyzing a patient's medical history, genetics, lifestyle factors.
Right.
AI can help predict how different treatments might affect them.
Exactly.
So it's like tailoring the treatment to the individual.
Yes.
Rather than a one-size-fits-all approach.
Mm-hmm.
That's incredible.
Yeah.
Are there any other ways AI is being used in healthcare that, might surprise people?
Definitely.
AI-powered chatbots are becoming increasingly common.
Okay.
They can provide patients with information, answer their questions, even help them schedule appointments.
It's all about making healthcare more efficient.
Yes.
And accessible.
And accessible. And there's that ambient listening system you mentioned earlier, right?
Oh, yes.
The one that can transcribe conversations between doctors and patients. That sounds like a game changer for reducing paperwork.
It is.
And freeing up doctors' time.
Exactly. It's just one example of how AI is streamlining workflows and improving patient care.
Okay, so we've seen how AI is transforming robotics in healthcare. What about natural language processing? We touched on how transformers have revolutionized this field.
Yes.
But how is that playing out in real-world applications?
Well, ChatGPT is a prime example.
Right.
It's able to generate this human-like text.
Yeah.
And engage in these natural conversations.
They're pretty wild.
The implications for communication and content creation are huge.
They are.
These models are trained on vast amounts of text data, allowing them to understand the nuances of language and produce incredibly accurate translations.
And speaking of language, I remember reading about how AI is being used for sentiment analysis.
Oh, yes.
Analyzing text to understand
Right.
the emotions and opinions behind it.
Sentiment analysis is a powerful tool.
It is.
It has applications in social media monitoring, brand reputation management,
Okay.
even gauging public opinion on important issues.
So it's like having a finger on the pulse of how people are feeling.
Exactly.
So we've got robots that can move like humans.
We do.
Algorithms that can potentially diagnose diseases earlier.
Potentially.
And models that can understand and translate languages.
Amazing.
With incredible accuracy.
It is.
It's all pretty mind-blowing. But there's one more application of AI that I found particularly intriguing.
Oh.
It's about data compression and the very concept of meaning.
Ah, yes. One of your sources explored this fascinating connection.
It did.
It delves into Kolmogorov complexity, which is this theoretical measure of the shortest possible description of something.
It basically says that the more you can compress something, the more patterns and structure it contains.
Exactly. And the more patterns and structure something has, the more meaning it can potentially convey.
Right.
Think about how data compression algorithms work.
Yeah.
They find and exploit patterns to reduce redundancy. Our brains do something similar when we make sense of the world.
Right. We filter out the irrelevant details.
Yes.
Focus on the essential information that helps us understand our surroundings.
Exactly.
So is it possible that the emergence of meaning itself is a kind of compression process in our brains?
It's a fascinating question, isn't it?
It is.
It suggests this deep connection between information, compression, and the very nature of meaning.
Right.
And it raises all sorts of profound questions about consciousness and how we perceive reality.
Wow. That's a lot to ponder. It seems like with every answer AI provides, it also opens up a whole new set of questions.
It does.
Makes you wonder what the future holds.
It certainly does.
Well, this has been an incredible journey. We've gone from the nuts and bolts of AI hardware to the philosophical implications of meaning and consciousness.
Yeah.
It's clear that AI is more than just a technology.
It is.
It's a force that's shaping our world.
It is.
In profound ways.
Profound way.
It's been a pleasure diving into these sources with you.
It has. It has.
It's amazing how much insight and intrigue can be found in just a stack of information.
It really is. It really is.
And to our listener, thank you for joining us on this deep dive into the world of AI.
Yes. Thank you.
We hope you've gained a new appreciation for this incredible technology and the possibilities it holds. Until next time, keep exploring.
Keep exploring.
Keep learning.
Keep learning.
And keep asking those big questions.
Those big questions.